Our next speaker is Alan Galley. Alan completed his MSc in Geology from Western University and PhD from Carleton University. After beginning his professional career as a geological consultant, he spent the next 27 years with the Mineral Deposits Group at the Geological Survey of Canada. After attaining a position as Senior Research Scientist, he became the GSC Minerals Director until leaving the GSC in 2011. During his geoscience career, he focused first on understanding the distribution of the greenstone-hosted gold systems in the Canadian Shield, then on the study of both modern and ancient volcanogenic massive sulfide deposits and the formational process. Alan is presently the Exploration Director for the Canada Mining Innovation Council.
Thank you very much, and thank you to the Toronto Discussion Group for inviting me here today. It's always a tough act following Catherine, but we'll see what we can do here and try to keep people's interest while the beer is already coming into the back, I think. So we're taking this, I got to mention first of all that I'm not an expert in data integration. What I am is a research manager. And in this particular case, we're going to be using the NSERC, Canada Mining Innovation Council Joint Footprints Project as an example of how you have to develop the proper workflows and get those in place, and again, and get the buy-in from the people in the project. In this case, we're talking 18 universities, 45 researchers, and 30 companies, in order to be able to point and achieve what you're trying to do. And in this particular project, the whole project is about how do we better integrate multi-parameter data sets in order for companies to more effectively develop deep exploration technologies. Oh my goodness, oh, that came. Anyway, so what we'll talk about is we'll look briefly at the data integration problem. And again, I'm looking at it from the point of view of a research manager. There's people in the room here that know much more about data integration, including Vince Gary, who's going to be is part of the Footprints project, and Hernan. By the way, Hernan, did I ever get your TGI3 project products there? Oh, yeah, it always comes back to haunt you. And then what I'll do is I'll quickly take you through the Footprints project in the context of data integration. And then we'll look at some of the components, again, that workflow that you have to develop both on the human side and on the technology workflow side with respect to being able to open up some new innovation avenues, which is what this is all about. There's lots of people working on data integration right now. There's lots of companies and very smart people in companies that are doing some really excellent work. What people are paying for us to do in this project, these 30 companies, is to come up with that random difference, something that nobody's looked at before, in order to take them in another direction, perhaps even a step change direction with respect to deep exploration. And that's what brings me into this last topic, this idea of adding little bits of randomness to the data integration equation. So again, we're all familiar with the history working up to where we are right now. That, of course, a big breakthrough in this first step towards integrating data was this development of robust GIS software. And what this allowed us to do is take data sets at various different scales and be able to stack those data sets within a constrained geographic area. But the optimal word there is stacking, is that although this was an extremely useful product, it basically took what we used to do with paper products and it put it into a computer-generated modeling world, but it was still stacking the data. The data is not talking to, the different data sets are not talking to one another within this particular type of scenario. And the next stage, of course, was then being able to take those 2D GIS products and develop them into forward modeling and in a 3D space. And that was incredibly important. But again, what we're looking at is different components in that 3D space, which takes us sort of to the next breakthrough. That's an important part of this project, and that's when people like Doug Oldenburg at UBC and his crew started to come up with some very robust algorithms for data inversion, for geophysical inversion. And so instead, again, now that we're not looking at 2D space anymore for this geophysics, for field potential data, but rather now have algorithms in place that allow you to generate a depth function or a depth component to that geophysical expression, but in an unconstrained manner, because basically what we're doing is we're looking at magnetics, so we're looking at gravity, and now it turns out we're looking at EM from the newest codes coming out of UBC, and that's being done in either 2D or now in 3D space. But again, when we take that inversion data and we add it to the geological data and we add it to the geochemical data as shown on this diagram, we're still looking at separate data sets within a particular geographic regime. So that's sort of the first part of the problem here, this idea of how can we better integrate, which basically is this idea of what kind of space can you create and what the algorithms can you generate that will actually allow the data to talk to one another, to give you some incremental value of that multi-parameter data set. Now the geochemists, as Linda has been explaining, have been doing this for a number of years. In looking at multi-element data and how you can actually generate principal component analysis to do that. So it's not a new concept by any stretch of the imagination, but now instead of just doing it for geochemistry, we want to include geology, geochemistry, geophysics, petrophysics, everything, all in one package. And that's what this project's about. I'll show you in a minute. The second challenge that I'm basically pushing on the data integration group is this idea that, so I can find there it is, that this is the space here that most of us are working in. And if we look at in an ore system criteria space, this is basically, if we look at all the major ore systems that are basically known in Canada and globally, is that we know probably at this point in time about 80%, perhaps even 90% of the criteria that we need to explore for these systems. Again, the criteria we know are all separate bits of information with respect to geophysics, geology, etc. But using that, what happens then is that we start to do, if we start to use statistical analysis to generate an environment to integrate that data, is that we're taking those known criteria and thereby setting limitations on the statistical methods that we're using. And basically this is called the deterministic space. So in other words, we're controlling how that data is being used by preconceived ideas of what we think the ore system characteristics are. So what we're really interested in are these two little bits off the side here. And these are basically the little bits that usually get chopped off because they represent noise. And what we're doing, the whole idea of this is when you're looking at developing new exploration criteria, is you're trying to minimize the noise and maximize that ore system signal. And so by doing that, what they say is, well, we got these fuzzy bits on the edge and we don't understand them, so let's get rid of them because it makes it a lot clearer to work in this middle bit. And so the challenge I've given to the team, the footprints team, is that I'm really interested in those little bits on the side because they might represent 10% of the volume of knowledge, that total volume of knowledge we have about an ore system. But with respect to value added, they probably represent about 90% of the impact we could have in changing the way people explore in a deep exploration environment. And one of the ways we can do that, rather than sticking in a deterministic space, is we're going to start talking about something that Hernan brought up, this idea of non-deterministic stochastic analysis. I can never get this right, stochastic analysis. So Footprints project. So the whole concept of this project, this is a $13 million 5-year project, again 30 sponsors. It's a joint project between the Canada Mining Innovation Council and NSERC. Is that this whole concept again is that we have all this data that we can layer up, and each of these data sets identifies a certain bit of the criteria that we use to identify the physical and chemical characteristics of an ore system and the extent of that system. So what we're trying to do then, as I say, is we're trying to gather those together and actually flatten those data into a single layer in which the data talks to each other and allows you to generate new criteria or new rules for looking for these deposits. So in short then, we're looking to better constrain 3D inversion modeling through multi-parameter joint inversions, identify obscure, these are the sides that I showed you, the obscure overlapping physical and chemical characteristics that further define the nature and extent of the ore system's footprint. And by doing this, which is basically up to knowledge at that point, is develop better 3D vectoring tools towards the hidden economic core of various ore systems. So to create the environment in order to do this effectively, what the Footprints Project did is we had the companies, 3 companies volunteered their existing mine areas, and one was the Canadian Malartic gold system, which is an Archean bulk tonnage gold system, 400 million tons of gram gold, a very different type of gold system that people are used to looking for in the Archean, and it was one that our group, our consortia of companies chose that they wanted one of the areas to focus in on so we could develop more robust criteria for this type of deposit. The second is Cameco's Millennium MacArthur trend, the richest uranium trend in the world in the Athabasca Basin, Saskatchewan. And the third is the Highland Valley Copper Camp, which is essentially Teck, 2.5 billion tons of copper moly ore, original resource reserves, largest in Canada and probably one of the largest in North America. So we have 3 different types of ore systems that we're tackling here. Now, in order to develop some kind of a way of communicating between the research teams of these 3 areas, we also developed a matrix where we had experts that actually sit in different teams that work on all the different areas. And so this is the geology, the lithogeochemistry, mineralogy, all listed here, ending up in the inversion modeling, which actually should sit up there at the nexus point, which is the data management, integration, analysis. And of course, that is the nexus point for the project, but the pointy end of this whole thing, and nobody can lose track of this, is that we're out to develop new exploration tools and models through this process. Now, this matrix, and I work as I said, as a director at the GSC, where they try to impose matrix management on it, and I'm still going through therapy for that. So when we developed this thing, I realized, God almighty, we have another matrix. And we've got, as I said, 45 researchers, we have 18 universities, we have 30 companies that we encourage to be involved in the direction of that research through being subject matter experts, and they're all kind of swirling around. And I finally realized that the first thing we have to do if we're going to gain the objectives of the project is develop proper workflows for the people in the project. Now, academics don't like to be boxed in commonly. Whoops, somebody waving my arms. And so there's a bit of pushback on this to begin with. And so, rather than call these organization charts for each of the 3 research areas, they're basically workflow charts. And what people finally realized is it allowed all the students and all the researchers to understand where they sat within a particular research space, who are their partners and who they should be talking to better understand how petrophysics links with the geophysics, links with the lithogeochemistry. And more importantly at all, it shows how they're all focusing towards one goal, and that's feeding that common earth model that allows us to develop an internally consistent database that allows us to develop the new data integration tools and do the constrained inversion modeling that's required to see a success of this project. So that was the people workflow, like Catherine mentioned, is that this is an incredibly important part of a huge project, whether it's an exploration project, a mining project, or a research project, is that everybody has to know why they're important, how they fit in the system, what their common goals are with everybody else in the project. And once you achieve that, all of a sudden everything starts to fall into place very quickly. 10 minutes? Okay. So the other part of the workflow then is this idea of in order to push forward on data integration, there's components that all have to be in place. The data management platform, and people have talked about Cameco showed all the effort that had to be put in to develop an appropriate, robust data management platform. In our case, we're using Miro Geoscience Integrator. It's a relational database that was actually developed in a mining environment for multi-parameter mining data, geotechnical data, and now we're transferring that into a geoscience world. So somebody asked earlier about what are the connections we can start making between geotechnical and geological, and this is one of the things that we're hoping to do here. So having that data management system, of course, allows us to properly feed internally consistent data into a 3D common model, and that becomes a basis for drawing out your data to do the statistical analysis and to start playing with the inversion modeling. Now, a common Earth model is not a new concept, and it's something that many companies are using nowadays in order to have a visual, basically a visual platform in which they can take all the different types of data as shown here, stick it into one space, again, to make sure that all the data can talk, is in a position to talk to one another, is internally consistent, and then allows you to start playing with that in a loop between a statistical group who keep on generating the new algorithms, feeding them back into the common model, and that goes out into the inversion modeling world where they start to develop new codes from that. So in maximizing our ability to do that data integration, and again, these are the points that have been made by previous speakers. It's important. It's this idea of the data QA/QC that's done within the data management space. And this is extremely important when we're working with legacy data from 3 different companies, and in the case of Highland Valley, over 75 years. Characterizing data uncertainty, I'm not going to talk about that a lot today, but that is something that's usually ignored. People talk about data accuracy and precision. They don't talk about the uncertainty of the data. So how do you measure, how do you quantify the certainty of a geological map, as an example? It's easy to do with geochemical data, but when you start working into potential field data, you start working into geological data, which becomes a little more subjective. How can you tag a quantitative uncertainty index to that? This idea, again, of how can you, if you're going to be inverting data, how can you integrate potential field and point data? And we'll give an example of that in a minute. And then this idea of the data is scalable. Potential field data is usually collected at a larger scale and at a different sample density than your lithogeochem data or your rock property data. And because of this reason, it's essential to start having the ability to develop proxies for your data in order to populate these sparse data sets so that you start to have consistent densities between two different types of data to allow you to integrate them. Okay, so these are right into the joint inversion challenge then. This idea is a principal thing, and Hernan stressed this, and I agree 100%, that the first thing we've got to do to constrain geophysical inversions is to be able to integrate rock property data into both magnetics and gravity as a start. And so in order to do that, as we know, you might have 200 or 300 drill holes in a project, of which maybe 10% you'll have rock property data for. So how can you develop proxies for rocks data that will take in all of the information that you require in order to make a robust inversion model? And so we'll go on in here. So again, we're trying these, and the group is trying this in 2 different ways. When we're looking at the statistical analysis, the first way is what you could call probably the more deterministic way. Again, this idea of using weights of evidence as a basis for starting a statistical analysis. But the idea is to look at some of the packages that are out there now, R, K9, or NIME, SOM, K-means. These are all standard software packages that we're testing by using the multi-parameter data sets that we've generated at these 3 project sites. And so some of the things you're looking at is this idea of making application independent in the end, so that when we deliver a product at the end, you don't have to buy a specific piece of software to be able to do the analysis. The other thing is to get away from grids. The idea is to start looking at volumetric containers that contain your data at different scales. So these are 2 of the things that we're playing with here within sort of the deterministic space. But what I want to show very briefly, and again probably so briefly that I'll butcher it. I'm glad Ernst isn't here. He'd probably have a fit. But there's some very bright people out there right now that are doing these hybrid deterministic stochastic common Earth modeling scenarios. Ernst Schletzler is at the GSC along with Gilles Belfleur with the seismic team there, and then Jamir Shamsapur is at UQAM and has already written a very interesting paper on this type of thing. So very briefly, what we're trying to do here is we're trying to use geological constraints to begin with to generate proxies for your rock property data, and then use that combined data set of real data and proxy data to be able to test and constrain your gravity inversion. So basically the first thing they do is they take the gamma, the density that's generated from the gamma logs, and this is again Vince Gary's group that did this. And the idea then is that then you have to locate that data and the lithogeochem data. In this case, the closest thing you get to density is the iron composition of the rock, and you have to locate that within a geologic space. And in doing that, what they did is they got away from using Cartesian coordinates, and they actually used the contacts, the curved contacts of the geological framework in order to develop curvilinear volume spaces of which they could start to populate those voxels with multiple data and then start to solve those the problem of compatibility by using co-creating. And again, I won't go into the details right now, but obviously this is going to take a huge amount of computing power because you have to solve the equation for each of these voxels simultaneously. So this is the big challenge right now, and there are companies out there that are going from having to use supercomputers to do this to using a tablet. So we're not that far off from being able to do this as a company. The idea then, as I said, all they did then is they take that generated data set that becomes much more refined than just using the sparse rock property data that you had, and then you combine that in that same space but in a non-deterministic manner with your gravity data. And then the last diagram there is basically what would be one of your unconstrained gravity inversions, and you can compare that to the middle, which gives you a much more constrained way of looking at that gravity by generating density information. Lastly, if you go to a completely non-deterministic approach for data analytics, and so this is the idea is that you don't constrain your data at all. All you do is you let your data run within a set volume. You pack your data, your multi-parameter data into those set volumes, and you let it interact through various algorithms. So again, very simply, you take your data sets, you make sure that they're internally consistent, you dump them into a matrix for data consolidation, you run it through your analyses, and then the data sets the new rules, the new criteria that will come out the other end. And then when you do that, you feed that back into your Common Earth model for validation. Does it work? Doesn't it work? If it doesn't work, you go back out again and you start again. And so what you're doing is you're setting up a framework now where you're almost in an environment of machine learning. And so you can start bringing in that new sort of element of a machine that can start thinking and start working its way through these problems and coming out with non-deterministic solutions. I should mention, I'm sorry, at the bottom here, these are the companies that we're working with in this non-deterministic space right now. And it's interesting, ones like Bearing Point and Pitney Bowes have nothing to do with the mining sector. And this brings me, I think, to the point that when you're looking for these non-deterministic solutions, we have to go outside our industry and look at what other industry sectors are doing, such as Kmart. I mean, Kmart takes all this data and they find cost trends by looking at what look like disparate pieces of data. Okay. Anyway, I just want to very quickly then, this is the research team that is working on this problem right now within Footprints, and these are our industry collaborators, and it's going to be a lot of fun over the next few years. Thank you.